Today's video is on chemical bonding. This is chemical bonding 2. In this lecture, we're going to look at how to draw Lewis structures for chemical compounds. This is a lot about process, more so than memorization, so it's important to write down examples of how to get through a Lewis structure properly. A Lewis structure is a structural formula. It shows the arrangements of atoms in a molecule and combines electron dot diagrams that we did in an earlier section. By structural formula, we mean that it shows the connections between atoms. So we defined that in our last video. A regular chemical formula shows us how many atoms and what those atoms are. The structural formula adds the additional perspective of showing how the atoms are actually arranged as they group together during the chemical bonding. To do a Lewis structure, to draw a Lewis structure, it's important to know what kinds of atoms you have present in the molecule. So we have to look at a chemical formula that's going to provide that information for us. So this is going to come from either formula or name. If you're given a name, you're going to have to write a chemical formula to make sure that you've got the proper number of atoms present. We draw electron dot diagrams for each type of atom, and we do that for a reason that will allow us to check ourselves at the end. And we use the dot diagrams to help determine the total number of valence electrons in the molecule. And this is a very important point. We're going to come back to this, which is the reason for the asterisks. We then arrange the atoms in a reasonable way. This is going to take some practice, but some general rules of thumb that we can use is that we're going to go at the lowest electronegativity at the center. So we have to consider electronegativity, low value in the middle of the molecule. Hydrogen can only bond with a maximum of 2 electrons. So when it's chemically bound and it's 1s level full, it has 2 electrons. So it can never have more than one bond, since every bond is 2 electrons. So it's impossible for hydrogen to be at the center of a molecule. It always has to be on the edges or on the periphery. Carbon, on the other hand, carbon has the ability to form 4 bonds, pretty much always. And because of that, it has a wide range of bonding abilities, and it's always going to be in a central position whenever it's present. And sometimes also it's possible to look at the dot diagram for the element to assist in decision making, but not always. And this is usually not a good rule, but there are times when it can be used. The reason it's not a good rule is that Lewis dot diagrams don't show where the electrons are coming from or where they're going. They just give us numbers and arrangements. Okay. Once we have the logical arrangement of atoms in the molecule, we put those together and we add unshared pairs of electrons so that each nonmetal that adheres to the octet rule has 8 electrons. So we put our atoms together in a logical way, we connect them with electron pairs, and then we add unshared pairs of electrons so that each nonmetal follows the octet rule. Octet rule is 8 electrons, or a noble gas configuration. Atomic numbers 1 through 5 will not follow the octet rule unless they acquire some electrons from somewhere else. The reason for that is they just don't have enough electrons. Elements in period 3 and higher most often follow the octet rule, so we apply the octet rule first. But sometimes they're permitted to have more than 8 electrons, and the reason for that is in period 3 we're looking at energy level 3, and we end up with a D sublevel. And if we go to period 4, we get an F sublevel. After you've arranged everything, you count your total electrons used in the molecule. If it's the number, if it's equal to the number that you were supposed to use, that you had available to you as valence electrons, then you have a possible or plausible structure. So let's show an example of this. We've got silicon tetrachloride. This is a covalent compound, we have two, actually a metalloid and a nonmetal. Silicon tetrachloride is going to have the chemical formula SiCl4. Now we draw our electron dot diagrams for this. We have Si first. Si is going to have 4 dots. I'm going to do these dots in a different color because I don't want my dot on my eye to look like an electron. So we have a pair of s electrons and 2 p electrons. We also have chlorine, and each chlorine has 7 dots. Okay. Now, if you don't remember how to get the number of electrons in the dot diagram, silicon is in family 14, or group 14. Chlorine is in group 17. So both of these are p block. In the p block, look at the second number, the second digit in the group number, and that will tell you the number of valence electrons that are present. So all these are, this is not the total electrons, this is the valence electrons that are present. Okay, within a range, actually we need to do a little bit more than this. We're going to count electrons. We have one silicon atom. So we have 1 multiplied by 1, 2, 3, 4 electrons equals 4 electrons supplied to this molecule from Si. We've got 4 chlorines, 4 SiCl4. So we've got 7 times 4 would be 28 electrons. Each chlorine atom has 7 multiplied by 4 atoms. It's going to give us a total of 32 electrons as we add those together. Now, these are the electrons that we have available as valence electrons to gain, lose, and share, and here we're going to be sharing. Next, we try to arrange the atoms. We've got our Si is going to go in the center. Reason Si goes in the center, Si is lower electronegativity, is the best reason. Our chlorines we're then going to arrange around, and I'm attaching each of them with a dash. Okay? Each one of these, I have a dash like this. This represents an electron pair. It is a covalent bond. So we have 4 covalent bonds there, and 1 to each chlorine. We then add electrons to each atom, checking to make sure that each atom has up to 8 electrons. So our silicon in the middle, we have 2, 4, 6, 8 electrons. The chlorine has 2, 4, 6, 8, 2, 4, 6, 8, and we repeat that on each of the other chlorines. So that gives a total of 2, 4, 6, 8 electrons per chlorine, or 8 electrons here times 1, 2, 3, 4, 8 times 4, 32 electrons used. Notice that our number used and our number available are the same. So we'll consider that a valid structure. Had they not been the same, we would have said that the structure is not valid. Okay, let's try another. Next is iodomethane. Iodomethane is not part of a chemical naming system that we're going to be covering in this class. This is going to be ICH3 or CH3I, either way would work. I'm going with this because I've already written it. We have sorting out the molecule into atoms. We have iodine, we have carbon, and we have hydrogen. Iodine is in group 17, so it has 7 dots. Carbon is in group 14, so it has 4 dots. Hydrogen is in group 1, 1 dot. Alright, we have 1 iodine. That's 1 times 7 electrons equals 7 electrons. We have 1 carbon. 1 times 4 electrons. 4 electrons. And then we have 3 hydrogens. 3 times 1 electron, 3 electrons. That's going to give a total of 14 electrons. We need to arrange in a logical way. Hydrogen can never be in the center. Carbon is always in the center. So we're going to place carbon in the central part of the molecule. We're going to arrange the other atoms around. In this case, it really makes no difference where you put them. So we've got hydrogen, hydrogen, hydrogen connected with bonds, and then we've got iodine. In our next step, we look to see that we have an octet on each atom that follows the octet rule. Carbon is the first that has 2, 4, 6, 8 electrons. Iodine has 2, 4, 6, 8 electrons. Hydrogen does not follow the octet rule. It only gets 2 electrons, and each one of our hydrogens has 2. We now count. We've got 2, 4, 6, 8, 10, 12, 14 electrons. 14 available, 14 used, valid structure. Next example. Boron trichloride. Boron trichloride is going to be BCl3. We have boron and we have chlorine. Boron is in family 13, so it has 1, 2, 3 valence electrons. Chlorine is in family 17. It has 7 valence electrons. We have 1 boron. That's 3 electrons. We have 3 chlorines. 7 times 3, 21 electrons. Means we've got 24 electrons available. We then try to arrange. Boron has the lower electronegativity, so we place it in the center, and we put chlorines around. We connect with single covalent bonds, and then we check to see who gets lone pairs of electrons. The chlorine follows the octet rule. So we add electrons until each atom gets 8. The boron is atomic number 5. And according to my rules of thumb I gave you earlier, the first 5 elements don't follow the octet rule. So this atom does not get 2 extra electrons. It gets what we've given it, and that's it. So this is not going to follow the octet rule. We then have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. 24 electrons, 24 electrons, valid structure. Next example. We're going to go with a polyatomic ion this time to see how to handle charges. So sulfate has the formula SO4, and it has a -2 charge overall. So we look at our formula. We've got sulfur and we've got oxygen. Our sulfur is in group 16, so we have 1, 2, 3, 4, 5, and 6. Our oxygen, also in group 16, so 6. We've got 1 sulfur, that's 1 times 6 would be 6 electrons, and we've got 4 oxygen, 6 times 4 would be 24 electrons. That totals to 30 electrons. But we also have 2 extra electrons, giving us our -2 charge. So these provide charge. So this would be 32 electrons. We then choose between sulfur and oxygen, which goes in the middle part of the molecule, or the middle part of the ion. And sulfur is the lower in electronegativity, so we place it in the center. We arrange our oxygens around the perimeter. We attach each with a single bond, and then each oxygen follows the octet rule, so we're going to give each oxygen 6 more electrons to supply 8. And the sulfur follows the octet rule most of the time. It already has its 8. And then we have 2, 4, 6, 8 times 1, 2, 3, 4. 8 times 4, 32 electrons. Those match, valid structure. The only extra thing we'll do with polyatomic ions is we'll put brackets around them, and we'll put the charge outside, stating that there's an extra 2 electrons. Next, let's do a positive ion. Ammonium is a polyatomic ion also that has the formula NH4 with a +1 charge. So we have a nitrogen and we have some hydrogen. Nitrogen's in group 15, so that gives us 5 valence electrons. Hydrogen's in group 1, 1 valence electron. We've got 1 nitrogen. 1 times 5 is 5 electrons from nitrogen. We've got 4 hydrogens. 4 times 1 would be 4 electrons coming from hydrogen. That totals to 9 electrons. But we've got a positive charge, so that means we're going to lose 1 electron, which takes us down to 8 electrons. Nitrogen has to go in the center because hydrogen cannot. So we place nitrogen in the center. We arrange hydrogens around the outside with single covalent bonds. Nitrogen has an octet. Hydrogen doesn't get an octet. That gives 2, 4, 6, 8 electrons. Since it's an ion, we put it in brackets and we put the charge outside. It says 8 electrons used, 8 electrons available. Let's try one that has multiple centers. Ethane is going to be C2H6. In C2H6, we've got, follow the same process, we've got carbon and we've got hydrogen. Carbon is in group 14, 2, 3, 4. Hydrogen's in group 1, 1. 2 times 4, 8 electrons being supplied by carbon. 6 times 1, 6 electrons being supplied by hydrogen. That's going to be a total of 14 electrons. We know our hydrogen can't go around in the center, and our carbon has to, so our only way to get the carbons in the center is to connect them to each other. And then we're going to put the hydrogens around the outside, distributing them evenly. Connect with single bonds. None of the hydrogens receives an octet. They only get 2 each. That's the case here. And then each carbon gets 8, 2, 4, 6, 8, 2, 4, 6, 8. So 8 electrons adjacent to each carbon. Notice that this pair in the center was counted twice because it supplies, these 2 electrons belong equally to these 2 carbons. So this is 2, 4, 6, 8, 10, 12, 14 electrons, valid structure. All right, then we have oxygen gas. Oxygen gas takes the form of O2. We have oxygen, nothing but oxygen. It's in group 16, so we've got 6 electrons. There are 2 of them. 2 times 6 is 12 electrons total that we have available to use. In a diatomic molecule, 2 atoms of same element, the only way to connect them would be side by side. So we've got, or directly connected to each other. So we've got an oxygen connected to an oxygen by a single bond. We then supply each oxygen with enough electrons to make it have an octet. So that would be 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. We total this up, 2, 4, 6, 8, 10, 12, 14 electrons. These do not equal. This is not a valid structure. So then we have to decide, what do you do if you've used too many electrons? We used too many. And the answer to that question is that we go to another type of chemical bond, which is, it's not really another type, it's just a new situation. This is a single covalent bond. So here's what we do. If we've used too many electrons, we insert a double bond next. Double bond that's going to equal 2 shared pairs. So we've got 4 electrons in between the two oxygen atoms. We then again complete up to 8. 2, 4, 6, 8. 2, 4, 6, 8. That gives us 2, 4, 6, 8, 10, 12 electrons. Matches 12 electrons. This is a valid structure. Okay, so our method here is going to be, if we use too many electrons, we're going to start inserting multiple bonds. Now, besides double covalent bonds, we also have triple covalent bonds. And this would be 3 shared pairs. Whenever we have shared pairs, the nuclei that are involved in the 2 oxygen atoms, for instance, are mutually attracted to this negative area. So we have positive nuclei attracted to negative electron cloud space in between. The more electron pairs we have in between, the shorter the bond. So when we're talking about the length of the bond length single is greater than double is greater than triple. So a single bond is long, triple bond is very short. If you get too short, such as if we try to do a quadruple bond doesn't fly because the bond gets so short that the nuclei begin to encounter the mutual forces of one another, and they end up repelling. So the end result is that, as far as we know, there is no such thing as a quadruple bond. It gets too short, becomes unstable. Okay, so when too many electrons have been used, we add multiple bonds, double bonds and triple bonds, and each additional bond lowers the total number of electrons in the Lewis structure by 2. So if you put in one double, lowers used by 2. Two doubles, or one triple, lowers by 4. So when you look to see, when you draw the molecule with single bonds, then check to see how many electrons that you have used. At that point, you can make a decision about how many multiple bonds you want to put in to lower your number by the amount that you need to lower it by. And also, you have to make the decision of where to put them. Let's try another, carbon dioxide, CO2. We know with this that we've got carbon and we've got oxygen. Carbon is in group 14, so it has 4 dots. Oxygen is in group 16, 6 dots. 1 carbon, 4 electrons. We've got 2 oxygens. 2 times 6 would be 12 electrons. 12 and 4 would be 16 electrons total. We know carbon has to go in the center. Place our oxygens in. We put in single bonds. It's important to put the single bonds in first. You then give everything an octet, because carbon and oxygen both follow the octet rule. So make sure that they all have 8. That gives 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. Now, it's important to do the single bonds, because the single bonds, even if it's not the right structure, the number of electrons used tells you what you have to do. So we've used 20 electrons. That's 4 extra. So we need to lower our number by 4. We can lower our number by 4 by inserting 1 triple or 2 doubles. We're going to choose 2 doubles because it's more symmetrical, and there's actually other reasons why we would choose that, but we're just going to say try to be symmetrical when you can. So I'm going to insert double bonds between the carbon and each oxygen. That gives the carbon in the center 2, 4, 6, 8 electrons, and then we have 8 electrons around each oxygen. 2, 4, 6, 8, 2, 4, 6, 8. And that gives us a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons total. That's 16 electrons, and this 16 electrons are equal, therefore valid structure. Okay, carbon monoxide has the formula CO. We've got an individual carbon. We've got 1 oxygen. One carbon times 4. 1 oxygen times 6. 6 electrons. 6 plus 4. 10 electrons. We connect the carbon to the oxygen. We give each pairs of electrons to complete an octet. That gives 2, 4, 6, 8, 10, 12, 14 electrons. So we're 4 electrons over. We need to lower our number by 4 down to 10. The only way to do that here, since we only have 1 spot to put a bond, is we can't do 2 double bonds, so we have to do 1 triple bond between the carbon and the oxygen. And I've got too many electrons there. Erase. It doesn't really matter where you put the electrons, the lone pairs of electrons. 2, 4, 6, 8, 10 electrons. 10 electrons, 10 electrons. 6 of the electrons are in bonded pairs. 4 of the electrons are in the form of lone pairs on each atom. Ethene. C2H4. Carbon, hydrogen, 2 carbons, 8 electrons, 4 hydrogens, 4 electrons, 12 electrons total. Our carbons, like in the ethane that we had earlier, the carbons have to be connected to each other. We put single bonds first, spread out the hydrogens, two, 4, 6, 8, 10, 12, 14 electrons. We're 2 over the 12 that we need, so we're going to insert a double bond between the carbons. That's the only place the double bond can go because hydrogen can't double bond. So we redraw carbon to carbon, double bond in between, then hydrogens to each. For each carbon, that gives 2, 4, 6, 8, 2, 4, 6, 8. So our number is correct around the carbons. Each hydrogen has 2. And then we count our total number for the molecule, 2, 4, 6, 8, 10, 12 electrons to 12 electrons, correct structure. All right, polyatomic ion, got carbonate, CO3 with a -2 charge. We've got an individual carbon, we've got oxygen, each with 6. We've got 1 carbon, 4 electrons. We've got 3 oxygens, 6 times 3, 18 electrons. This totals to 22 electrons. But we've also got a charge, so we're going to add 2 more electrons to give 24 electrons. Carbon in the center, oxygens around the outside. Give each oxygen 6 electrons extra to complete its octet. And carbon is going to get an extra pair as well. That gives 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. So we need to put in a double bond. It has to go between a carbon and an oxygen. It doesn't matter which one it goes between. Put in 1 double bond. That should lower the number from 26 down to 24. Give each atom an octet. This oxygen with a double bond is only going to get 4 lone pairs, 4 lone electrons, 2 lone pairs. And then this oxygen will get 3 lone pairs. And same thing for this oxygen. 3 lone pairs. That gives 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. 24 electrons is the proper number. Bracket around, and that's a 2 negative. Correct structure. That concludes the lesson on Lewis structures, and in class you will be getting some practice problems on how to draw Lewis structures properly.